3, 2, 1.
Hello, hi everyone. Welcome to episode 1 of actually episode 2. So episode 2 of 418 I Am a Teapot YouTube channel. In this episode, we'll talk about chapter 1 of designing data intensive applications. And what this book is all about, we talked about in episode 1. So why don't you give us like a brief outline again, Darpan?
Yeah, sure. There are 3 parts to the book, and because I read this book before, I can provide you some more context as well. So in part 1, it's mostly about theory and the fundamental ideas that underpin the design of this data intensive applications. I would say the part 1 is a bit boring to read because it touches a lot of theoretical concepts and not as much practical applications. In part 2, it gets more technical and it mainly focuses on moving data stored on one machine to multiple machines which are distributed across multiple systems as well. And in part 3, it's about dealing with data that is derived from other data sets. And so it kind of focuses on how do you combine multiple data sets maybe into one and then make sense of that. Also at the end of part 3, it discusses about the future of data systems, which I found pretty interesting. And the part 1, since it's going to be talking about the foundational ideas, I would let you take over that and explain what are the things that we'll be discussing in the first chapter.
I would have like a lot of questions on the part 2 and part 3 because I'm a bit familiar with part 1. It comes up in like job interviews and designing systems in architecture and all that. But part 2 and part 3, which is like I think more of infrastructure level understanding of the systems, I have to read and get to that. So let's talk about part 1. So part 1, the first chapter, part 1 has maybe more than, it has more than one chapter. Yeah, 4 chapters. So the first chapter, we'll talk about first chapter here. The first chapter talks about foundations of data system. And they're like primarily 3 foundations: reliability, scalability, and maintainability. And this all translates to how we are going to build an application, and if the application serves these 3 foundations, most likely it is a good software system design, right?
Right. And I was thinking maybe if you could define the 3 terms, the reliability, scalability, and maintainability in one line. So maybe I'll start with reliability and then you can go for scalability, and I can take care of the maintainability. And the focus is just like what we understand in one line about that word. So how I think about reliable systems are systems which continue to work under faults which are either user introduced or system introduced. So basically what are built, it should work even if things go wrong. What do you think about scalability?
So one line, defining it in one line, I think the author does a good job. But for me, like scalability is the functional correctness of the code does not change given there is a small variation in one of the load parameters, and the matrix actually still makes sense to the user experience. For example, I would say latency. So latency should not degrade as much even if our throughput increases a lot, which is like the number of requests coming to our server. And similarly, response time is one thing. Like even if the throughput is high, the application should be designed in such a way that it is able to perform in a given response time, and the user experience does not degrade as much.
Right, yeah. And for the maintainability, I think of it in these terms. If I write some code, then when I leave that team or the company, first, someone else should be able to run that smoothly.
Yeah, definitely.
And second, someone else should be able to add more features or able to extend that smoothly. If they are able to do that, I would consider that at high level a maintainable application.
Definitely, we don't want someone leaving the company and then we're looking into their code and no idea what's there. I think documentation is a very important part of maintainability as well.
Right.
Yeah.
And even before discussing these three concepts, the book talks about the fundamental idea of data intensive applications. And the reason given was that the raw CPU power is rarely a limitation these days, and also the CPU clock is barely increasing. However, the amount of data that we deal with, it is increasing in magnitudes year over year, and we are limited by how fast or how reliably we can process the data. So that is one thing, and second thing is that we are kind of web developer, at least we work with web, internet in general, and whatever we design or develop, it's got to be dealing with some kind of data. For example, we are not just applications developer. Whenever we design, we'll have some cache or some database or some queue, some monitoring solution. So because of this, it is very hard to call ourselves just an applications developer. All of us are data applications developers as well. I don't know if that's the correct word to say, but
yeah, it's very interesting that you bring these two things. Like the first part, where as far as I understand it, it means vertical scaling is now not a option to scale your systems, and horizontal scaling is, but when we scale horizontally, network becomes our choking point.
Right.
So we have to figure out a lot of different data principles that can actually make this horizontal scaling feasible. So and that happens because we have a lot of data flowing through the system, a lot of data stored in certain systems that needs to be accessed at some point of time.
right.
Yeah.
So the first topic that's being discussed in the chapter 1 is reliability, and just to reiterate, that is things continue to work correctly even when there are faults in the system.
Yeah.
And there is a distinction between fault and a failure. Fault is something that we could anticipate and maybe try to cope with them as well. Failure is just the system giving up at all, like, okay, I'm done, I cannot handle this anymore.
Yeah, this was a very important distinction, and honestly speaking, I had no idea these two are two different things. So the author says that the fault is good, but failure is bad, and sometimes we have to intentionally find faults in our system so that we don't have a failure. Which is a very interesting way of saying that we want to break our systems so that it is resilient, that it doesn't fail in situations that we don't understand.
Right.
Yeah.
And there is this also difference between hardware errors and the software errors. And when I was reading that section about hardware errors, I remember one video from YouTube. So in that YouTube video, a guy, he walks into a data center and he's trying to analyze the latency of the hard disk reads. So what he does is that he has one graph going on one side on one monitor, and then he goes to a hard disk and he yells at that. Because he yells at the hard disk, because of the vibrations around the hard disk, the latency actually got increased.
Oh.
Even though this is not a fault, it just kind of came to my mind, and then the author goes on to introduce the software errors. And while we are limited by what we can do with the hardware faults, with the software faults, we can do plenty of things to basically fix things. From even if they go wrong, we can try to self-correct them.
Yeah, I think hardware faults are very difficult to fix unless you replace or upgrade that hardware. And I think that might be really operationally expensive operation for any company.
Right.
But yeah, software is, I think, very lightweight and very easy to iterate. And software errors are something we should keep detecting and fixing as much as we can to keep our systems resilient.
Right.
Yeah.
There is also this section about human errors. So I'm curious if you had any example of a human error that you made.
Yeah. And it's kind of embarrassing, and I don't know if people from my previous company is watching this video. They'll be like, yeah, I remember that guy did this error. So I was testing something on staging. There was a software I was writing to mask certain phone numbers, and I had some sort of data in MongoDB. And in MongoDB is like a document-based database, and it has collections. And inside collections, we have documents, which are like records. So if you compare it to SQL, collections are like table, and documents are like rows. Right. And in staging, what I did is like just drop the collection itself rather than clean it, because now I'll have a new collection and then I can test the whole thing again. And when I was launching the same thing in production, I dropped the production collection. And it was not so bad because that collection was new. I dropped other collections as well to clean up the entire database, and many operational problems came up with that. And that's the problem of a human error, like where we don't have enough automation and review policies and review processes in how you actually move from staging to production. Like it's something that can happen anytime, and more automation is there, more we can eliminate human error. I don't know if you were looking for an example like that, but
yeah, definitely. Yeah. And so to avoid this, or at least to prevent this from happening, there was this point that we need to set up detailed and clear monitoring, so that we can assess our performance metrics as well as the error rates. And that kind of hit me into heart, because as part of my current job, that's all I did for, I believe, first 4 months. My job was to set up Grafana dashboards, and basically based on the telemetry that we are getting, set up the dashboards and then set up the correct alarm, so that if things go wrong, yes, we need to fix, but at least we get notified before our customers get impacted.
Definitely, like operations is a big thing in software engineering world, and operations, when it comes to operations, having proper matrix like monitoring for watching all the health of the system, and it's not enough unless that system can also alert if something anomalous behavior is happening in the system, or like something very obvious that it is an error. There should be an alert on top of that, and that alert is not enough if there is nobody to respond to it. So on call, having pager duties and all this sounds like a drag, like something like, okay, we have to do so much work, but it's so important for a system to be resilient and be like operationally excellent.
Right. And usually we associate reliability with things like if we go outside the software world, things like airplanes or the nuclear power station. So we generally expect all the applications to work reliably, but then there was this contradiction that, let's say if you are a startup, or if you are not willing to put much efforts just trying to make a system reliable, where it can just fail and very few people will be affected. Yeah, in that case you can sideline the reliability. But in all the other cases, you should be very considerate of implementing the correct reliability in your system.
I think the author mentions this, like the system should continue to perform correctly even if things go wrong. And there is some sort of gray area there, like what do you define as correctness and what do you define as something going wrong. Like there could be some sort of margin that you can keep there for correctness and error, and people rely on percentiles for those kind of things, like 99.9% fault tolerance. So that can actually make sense for someone in a startup. Okay, 99% is good enough, but some company like operating at the scale of, let's say, Oracle Cloud or AWS, they need to go further nines, like 7 nines or 8 nines to give their reliability.
That's right. And that actually brings to the next section, that is the scalability. So it talks about, even if your system is reliable right now, but maybe right now you have maybe 100 users or 10,000 users, but how about when you have 1 million or 10 million users? So even in that case, will your system work reliability? Not reliable,
like have some sort of correctness in the system.
Exactly.
And the correctness is not contaminated by the number of requests coming in, right?
That's right.
Like some of the customers are getting good responses, but some of them are not, because they are being served from a server which is like heavily loaded, something like that. Okay.
Right. So in that case, if you are going to design a system for scalability, we need to describe what do we mean by scale, or how do you define your scale or load or the performance of your system.
Yeah, and there are lots of metrics associated with this. Like there is a concept in the software world of service level agreement, and then there are service level objectives and indicators to measure if the objective is satisfied and the agreement is not breached. And they are generally, again, in terms of percentiles, like what is the response time? And the response time shows up as like, let's say 99.99 percentile. So 1 in, let's say 10,000 requests can actually not be within that SLA. So maybe one of the threads is performing really poorly on some particular hardware somewhere, but all other 9,999 should perform within a given agreement of, let's say, few seconds, right? And the same thing happens with latency, as I talked about earlier. Latency, response time. I don't know, are there other metrics that we look at generally?
At least I know, since we deal with a lot of threading, we keep track of the number of threads that we are using. Also, I remember we had a very nasty issues regarding the garbage collection. So things like, if you really go deep into the performance, then how often are you garbage collecting, especially in case of the JVM languages like Java? What is the GC pause
what
time?
happens if like the garbage collection is performing poorly? How like you can see, okay, garbage collection is not happening on a particular interval, but then how does it translate to degrading the performance?
Right. So what happens is that when in case of Java, whenever it is garbage collecting, it does something called GC pause, which is basically all the threads will be stopped. And the entire garbage will be cleaned up, basically all the non-reference memory points, and then your system will start
Latency
again.
will go up,
yeah,
actually.
So that could be, I think normally it takes about 1 or 2 seconds.
Yeah.
We had our system where it was taking 10 seconds. So for 10 seconds, system is just doing nothing.
Yeah.
And
so like latency and response time are like very good indicators, but they would not give the root cause, right? For then to determine the root cause, you need to look at all the other telemetries that you have in the system, and then like you could say, okay, latency is high, and at the same time garbage collection is going on for a long time. So maybe we are maybe there is a loop somewhere in the code that is creating so much of garbage memory reference pointer that are not being cleaned after executing that loop,
right.
But it needs to be cleaned at the time of garbage collection. So optimize the code and somehow like be able to clean just after maybe the method is done, instead of like waiting for garbage collector to collect it.
Right.
Yeah.
And this actually, so this is also mentioned in the book. This is about the percentile. So we got to know about the GC because of the percentile graph that we had. So we had graph for P99, and we were realizing that at every 24 hours there was a big spike in that, and which was happening on a regular schedule. So that got us curious, like, okay, why is that happening every 24 hours? And the percentile graph of the latency was the entry point to what was happening regarding the GC. And I think we could discuss about the percentiles as well, and what do they mean if we have them on the graph.
So as I was trying to mention like a few moments ago, so when I said like 99.99 percentile, it means like 1 in every 10,000 requests may not be at the same value where we are seeing other 9,999 requests at. So very simply speaking, in mathematical terms, take all the response times that you have, or like all the latency values that you have, sorted in a order of magnitude, and then look at the 99.9% value in that ranked order, and what is the value of that particular latency graph. So 50 percentile will actually be the median. So you can look at 50 percentile as saying something which is at the center of my entire latency measures, like all different latency data that you have collected. 99.9% would be the one at 99.9% of all the values that you have collected in that time.
Right. And also, so far we've been talking about latency for all this scalability, but depending on our system, and I remember the example of Twitter, that in case of Twitter, you deal with a lot of database writes.
Yeah.
So the performance measure, it changes from latency to the number of database reads or database writes that you go through.
Yeah, so latency and response time are very interesting because they are like something which is visible to the customer directly, and you can just have service level agreements on those values. But once you start digging into why your latency is going up or response time is going up, then you need other metrics. For example, one of the things could be the GC collection that you're talking about. Other things could be number of writes we are making to the database. And then we have to come up with lots of system designs, and I think maybe the author will cover in the next chapters. But there can be system designs of like, if you are hitting your database a lot for reads, why don't you have a cache? That introduces other problems of how do you invalidate the cache, update the cache, and all other things. But that can actually reduce the latency so that you can go and still scale to a particular limit that the customer is actually requesting for. And it happens like it even. Why are we introducing the cache? So we want to reduce the database reads. Now, what if the database writes are huge? Then you have to think about systems like, do you want to do write through cache, read through cache? So all those designs will come in depending upon how the system needs to be designed. And then there could be hybrid approaches. You have both the cache and the database serving for certain number of users. For example, in terms of Twitter, it was like, if a particular user has a lot of followers, then they have actually so many writes into the system because you have to insert the same tweet in all those followers timelines. So instead of doing so many writes for a big mega follower at the request time of the creation of the tweet, instead do it later, right? So there can be hybrid approaches. You take certain actions for certain types of users, certain actions for other types of users, and then again you have to be resilient. Again, go back to the reliability principle. Like, you have to have correctness in the system. While scaling, you cannot put something to scale the system better, and then you may have like data inconsistency in two different parts of the system.
Right, and I guess that's the overall theme of the entire book, that this book does not magically tell you that, okay, if you want to scale your applications to maybe 10 million users, how do you do that? Instead, it focuses on giving us the trade-offs. Okay, if you want to, let's say, introduce a cache versus maybe a read replica of a database, what are the pros and cons, and what are the trade-offs that you're making? So there is no magic scaling sauce, as the book puts it.
Yeah.
It depends on your architecture. Basically the answer is it depends on what you're trying to achieve. The throughput for, let's say, 1 million requests per second of very small size versus a request that's in 3 GB of size. So ultimately you're processing the same amount of data, maybe 3 TB or something in that same time frame, but as you mentioned, the requirements to build those systems, they are very different. So it also touches about, like, if you are a startup or if you want to iterate your solutions very quickly, in that case you might not want to put a lot of efforts in making sure that your system is scalable. Just do whatever works for right now, and then once you get to a scale, you can iterate over that. So basically, don't design your applications to match the Google scale from the start. You can start from...
Yeah, true. The book will say, okay, you are doing this, here is the problem. And here is another solution that can solve this problem. Yeah. But there is this problem with this solution, right? It just continues to go through that, like always talking about pros and cons. And ultimately the designers, like we are having this discussion and all that, we designers have to decide what's a good architecture for some scale that we are foreseeing in the future. And then that prediction of how much scale we'll see, like, and that depends upon like how much you want to be resilient, right? If you foresee something 5 years down the line, maybe you'll be resilient for a long time and do not have to change your architecture. And then actually the third foundation actually comes in very naturally here. Like, you can build something that can scale up to 5 years of time, but what after that? Do you need to rewrite your entire code? No. like the software system design should be maintainable and extensible, right?
Right.
And that's why you can like keep building on top of it.
Exactly. So the three aspects that you want your system to have is, first of all, let's say you are engineer, and then you have maybe team of operations people supporting your product, because it's quite complex. So make it easy for these operators to run your system, like have enough run books, have enough metrics, telemetry, so that they can keep running very easily. So that's on the operation side. Second thing is that, what if there is someone new who is joined your team and they want to do something with your product. So in that case, the overall architecture should be simple enough to understand, and all the complexities should be either removed or they should be abstracted, so that if I'm a new person, I just look at maybe two or three documents, 2 or 3 diagrams, and I'm able to understand that. And the third point is making it easy to extend your system in future. So kind of designing your system from the ground up, so that all the modules are not tightly coupled. Instead, they kind of work nicely with each other, and if you want to modify them for any unanticipated use cases, you can do that easily.
Yeah. And you abstraction, like I really love abstraction, because how many times do you have to worry about, how many times as a software engineer you have to worry about the hardware or the OS or the nitty-gritty details of different types of OS, right? It's very rare. Abstraction is like, I think, the best wonder in the world of computer science, and abstraction helps us like keep systems simple and very user friendly, very developer friendly, and it makes things evolve very easily into future.
Right.
Yeah.
And regarding the operability, I can talk a bit more about that, because since I work in the cloud space, so once we build a service, a lot of our focus is on operations, mainly because that service will go to multiple regions, and I believe right now we have 50 plus regions. So what we focus on in doing operations is that we have enough metrics so that we can monitor the health of the system, and let's say if the system goes into a non-recoverable state, we have enough tools so that we can go there and change something manually. Second thing is that we have very easy pipeline to make any security patches or any OS patches, and of course, being a cloud provider, you cannot go down, so the pipeline also take care of kind of rolling upgrades, so like your system is never going down at any point of time. And that brings me to the last point of the good deployment model. So you can kind of divide your entire deployment into multiple days. So day 1 you go to regions which are not heavily used, and then day 2, day 3, and at the end of the deployment, maybe it's day 5 or so, at that time you deploy to basically all the regions which are heavily used by all the customers. So having this kind of good practice and tools for deployment helps with the operations as well.
Yeah, and like if you have to do rolling deployments or rolling upgrades and all, it's very important that the systems are backward compatible, right? And the systems have this feature of maintainability, right? So it just means like all these foundations that we're talking about, like they do not operate in silos. There has to be a balance between all of them, and they work best if they are all these principles are like thought of together, right? We cannot just keep thinking about operability and not think about evaluability, because if we have like backward incompatible code, or maybe something which is not maintainable, we will never be able to have these rolling deployments, because we'll have to make so much code changes just to make deployments happen, or maybe shut the world and then do the deployment and then open back for business, right? So these foundations that we talked about in this episode, like and Martin Kleppmann talks about in this chapter, it's like they work in sync, and there is like a healthy balance between them, and it's not that it's required like in equal proportions. Depending upon our use case, like we can go to different aspects and maybe do more tinkering in one aspect than other, but it's required, like all of them should function together.
Right. And you cannot have good operations if your system is overly complex. So
Yeah.
basically, you should strive for making your system as simple as possible, and one of the ways of doing that is by abstraction.
Yeah.
And I wonder if you have any example of abstraction that you use in real life.
Yes, interesting question. All of us would be familiar with different design patterns, right? And one of the design patterns, let's say the builder pattern, right? Where you don't need to call the constructor and you build the entire object step by step depending upon what configurations you are getting from the system, right? So these frameworks that we see, like there are lots of good frameworks, Spring Hibernate, Spring Boot, and these frameworks are just abstraction over the lower Java code, right? And these frameworks actually serve a particular use case. And when we have to build a code, we don't have to worry about how the HTTP connection is being made. We just rely on the abstraction that is provided in these libraries, how to connect. Like Hibernate takes care of all the connection between your SQL database and Java application, and you just have to write higher level data access layer code. So these abstractions actually make things really simple, and it's very easy to understand if the coding is right and documentation is right and comments are there in the code. It makes very simple for new developers to come on and then start working with those frameworks.
Right. Currently, I work on a product and we are trying to offer the Postgres database as a service. And while I do not work on the Postgres directly, it's amazing to see the number of abstractions that database uses. For example, as an user, I just write a query like select star from a table and I get some rows back. I do not have to deal with how do I store the data on the disk, what kind of in-memory structures I need to maintain while running the database. If I have multiple clients trying to make a change at the same time, how do I handle that? If my host that's hosting the database, if it goes down, how can my database remain in the consistent state? I don't have to deal with any of that.
Yeah.
All right, so we just had a hardware fault in our camera recording system. Our battery reached to 0% and we did not have any alarms or any paging system. So I had to run back home, get the charger. Hopefully, fingers crossed, the system will work reliably. And
now it has a constant power source.
Right.
Made it a little bit resilient.
Right. Yeah. So where were we before this?
Yeah, I think we were on the verge of summarizing this episode. We talked about lots of good foundation principles, and these foundations actually run, they have to be thought about in a balance, in a sync way, and they cannot operate in silos. And then depending upon our requirements on how we want to design our software system, we may work on some particular aspect a bit more than the other.
Right. And just to summarize the three concepts, reliability would mean that our systems work correctly even when the faults occur. Scalability means that while your system can work reliably, when load factors change in your system, for example, number of users or number of concurrent read writes, things like that. So keeping the performance good even when the load increases. And lastly, maintainability is just making sure that your system is simple enough to understand, it is easy to extend, and it is easy to run.
Yeah, definitely. Very beautifully summarized in like few lines. And that's what this first chapter is about, of designing data intensive applications. It's about not just the functional requirements, which is the code should be correct and should work as expected, but also the non-functional requirements of foundations of data science, like security, reliability, compliance, scalability, compatibility, maintainability, and those kind of things.
Right, yeah, those are a lot of buzzwords.
Yeah, and we'll be coming back to these foundations again and again throughout this book, I guess.
Right,
yeah.
I guess that will wrap up the chapter 1.
Yeah.
In the next chapter, we'll be looking at the different data models and query languages.
Yes, I'm guessing the next chapter would be very traditional computer science, and we'll have a lot of fun talking about it.
Right.
Thank you so much for listening to this episode. Yeah.
Thank you so much and have a good day.
Yeah, adios.
Bye.